Okay, so this is the video for section 4.5, inverse functions in pre-calculus, and today's objective would be to find the inverse of a function if it exists. So, I'd like to begin this lesson with the formulas for both Fahrenheit temperature and Celsius temperature. So Fahrenheit, in terms of Celsius, would be Fahrenheit equals 9/5 Celsius plus 32. And now we have something similar for Celsius in terms of Fahrenheit. And that is, Celsius is 5/9 of the quantity Fahrenheit temperature minus 32. Now, we're talking about inverse functions right now. And inverse functions are two functions that will undo each other. And what I mean is, and kind of look at some of the factors and terms in these two equations right here. Do you see the factor 9/5? And then over here in Celsius, we see the factor 5/9. Doesn't 9/5 and 5/9, those are reciprocals, all right? And they undo each other. Also notice plus 32, and over here I think I have a minus 32. And of course, plus 32 and minus 32 also undo each other. So those two functions could be inverse functions, and we're going to be able to prove that they are at the end of this lesson. So what's the definition of inverse? Well, in a section earlier in this chapter, we studied composite functions, and we use composite functions to determine inverse functions. So inverse functions, okay? Number one, g of f of x would have to equal x. And that would be for all x in the domain of, and remember, x needs to be in the domain of f. It does not have to be in the domain of g. So for all x in the domain of f. And number two, f of g of x also has to equal x. And that's for all x in the domain of, and what's the internal function here? G. There's your definition right there. So let's take this Fahrenheit equation and let's write it y in terms of x. We're going to use function notation with x as our independent variable. So let's say f of x equals 9/5 times x plus the 32. And let's do the same thing over here with the Celsius temperature. So c of x equals, and this would be 5/9 times the quantity x minus 32. Now, in this function notation, we can really do the inverse stuff. So f of x equals 9/5 x plus 32, and c of x equals 5/9 times the quantity x minus 32. Show that these functions are inverses of each other. So let's just use that definition on the previous slide. We're first going to find f of c of x, and hopefully we get an x. So I'm going to take this outer function f, which is 9/5 times x plus 32, but watch what I write for this x right here. 9/5 times the quantity, whatever my input is, plus 32. And what's my input? It's no longer x like I see above. It is the expression for c of x, which is this 5/9 times the quantity x minus 32. Just like that. Now, if I simplify this, I should get x. So just think about your order of operations. Okay? PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. So the first thing I'm going to do is simplify the parentheses, but there's nothing I could do in there unless I wanted to distribute, and I certainly don't want to do that. So I'm going to go to exponentials. I don't see any exponents here. And then I'm going to do my multiplication. Oh, I see 9/5 times 5/9. And wouldn't the 9s and the 5s both cancel? And what do I have left? X minus 32 plus 32. And I'm going to show every step here. And now, just combine your like terms. What is x minus 32 plus 32? That's going to equal x. There we go. And there's no domain restrictions, so we're good right there. Okay, let's find c of f of x, and let's hope the same thing's going to happen. So I'm going to take my function c of x, and I'm going to write this expression, but do you see this x right here? I'm going to put a set of parentheses right there for the x. Because instead of c of x, I now have c of f of x. And f of x is the 9/5 x plus 32. So we're going to bring that down and put it in the parentheses right there. Now, if I simplify this, I'm hoping that I get x again. And I just do my order of operations. And this time, see that p? I can simplify within the parentheses because I have a 9/5 x plus 32 minus 32, which is going to make this whole bracket right here 9/5 x. So I have 5/9 times 9/5 of x, and then I do my multiplication, and I get that canceling I'm hoping I'm going to get. Again, the 5's cancel, the 9's cancel. What am I left with? The x. And there's no domain restrictions. We have just shown that f of c of x equals x, and c of f of x equals x. Therefore, Fahrenheit and Celsius must be inverse functions of each other. So inverse notation. Let's learn our inverse notation. So if I'm talking about the inverse of f, I write that, and this does not mean f to the -1 power. F is not a variable, it's a function. So when we see a function with a superscript of -1, we say this, the inverse of f of x, and what does that equal? It equals c of x. Okay? Now, the inverse of c of x, that equals f of x. And I want to make one more point one more time. The common mistake is people see this superscript of -1 and they think that is a negative exponent and they want to write this 1 over f of x. That is not the case because each of these, f and c, are not variables. They are functions. And this is simply the inverse notation of a function. F inverse of x, c inverse of x. Okay, now we're going to graph 4 minus x squared for 0 less than or equal to x, and x is less than or equal to 2. Now, I'm hoping you guys are getting to the point where you can visualize this parabola. And if you can't, you could always go to your calculator and graph it as y sub 1 equals 4 minus x squared, and then change your x window from 0 to 2, and then probably do a zoom fit, and you'd get a perfect graph. But let's try this like this. I'm hoping you all know what the parent function y equals x squared looks like. That parabola with a vertex at the origin. And then if I throw a negative in front of that x squared, that's just going to flip that parabola. So it's going to go from opening up to opening down. And then if I add 4 to that, it's going to slide my parabola with a vertex at 0, 0, opening downward 4 units up. Okay? And I'll also remember this is in the x interval from 0 to 2. So I'm only going to see half of that parabola. I can't even say half of it because I'm only going to see the parabola in the x interval from 0 to 2. And let's go to our calculator. That would look just like that right there. And you know, if I would have just graphed f of x equals 4 minus x squared in a set of real numbers, I would have had a parabola starting down here, coming up, hitting the vertex, and then going back down like this. And the y-axis would have been our axis of symmetry, x equals 0. Okay, so there it is. Now, I'm wondering, does this function have an inverse? Well, let's talk domain and range, because domain and range are very, very important to inverse functions. Do you guys agree that the restricted domain of this function was given as 0 is less than or equal to x, and x is less than or equal to 2? So I'm going to put that right there, okay? And I projected it down onto the x-axis so I could see the graph of that domain too. Now I can do the same thing with the y's right here. all right? If I project this graph onto the y-axis, there we go right here, and do you agree 0 is less than or equal to y, and y is less than or equal to, what is that? 1, 2, 3, 4. There it is right there, domain and range. Now, we're about to discover something very important about the domain and ranges of inverse functions and how they compare to each other. Let's get excited. So, does f have an inverse? Now, I introduced this, I think, in the very first section of chapter 4, when we talked about functions and then whether or not a function is one-to-one. And a one-to-one function is a function that passes the horizontal line test. Okay, so let's find a rule for f inverse of x if it exists. Okay, so let's just visualize the inverse right now. And you guys, I'm hoping you have an idea that inverses are simply reflections of each other over the line y equals x. So if I'm going to visualize an inverse function, I visualize the line y equals x, which is the line going through the origin with a slope of 1. And I'm going to do that as a dashed line just like that. Now, the inverse of f of x equals 4 minus x squared in this restricted domain right here would be the reflection of this graph right there over the line y equals x. And now with a few key points, I can do this reflection perfectly. Notice how I chose the point 0, 4. Okay? When we do inverse functions, all we are really doing is interchanging the variables. So if 0, 4 is on the original function, then 4, 0, 1, 2, 3, 4 would have to be on the inverse of said function, right there. Okay? And then inverse functions will always intersect on this line, y equals x. So do you guys see this point right here? Okay, it's going to go right there. All right, and now I think I have one more key point on my original function. Do you all agree that this is the point 2, 0? So what point would have to be on the inverse? Well, interchange those coordinates right there. That would be 0, 2. And now I can draw my curve. And that is my rough sketch of the inverse of f of x equals 4 minus x squared. And now take a look at the domain and the ranges here of each of these. Okay? And notice my f of x equals 4 minus x squared, and this bold curve right here is the inverse of f at x right there. Okay? Looks like a root function, doesn't it? Well, we'll figure that out a little bit later, though. Okay? Oh, so find a rule. So let's do that right now. Now, there's a very simple way to find a rule for the inverse of a function. And that is, do you notice on this graph up here, what did we do? We interchanged the coordinates. That just means every x becomes a y, and every y becomes an x. So I'm going to take this function f of x equals 4 minus x squared, and I'm going to interchange the variables. So this f of x, which is a y, now becomes an x. And this x right here becomes a y. And now you just solve for that y. And you'll have to excuse me, but I'm probably going to skip a few steps here. I think what I'm going to do is, could I add y squared to both sides? Why, yeah. And then I have this plus x over here on the left that I want to get rid of. So I'm also going to subtract x. So I know that y squared equals 4 minus x. Now, I haven't solved for y yet, but I'm getting closer. I've now got to get rid of this square. And how do we undo a square? With a square root. So we're going to go, the square root of y squared would be y. And on this side, you need to remember both your positive and your negative root. So I'm going to put a plus or minus out front. And when I take the square root of 4 minus x, I'm going to write that exactly the way we just said it. The square root of 4 minus x. Okay? Now, I've got a comma there because I want to start talking about domain and range stuff here, okay? So the domain of f is always the range of f inverse. So right now, if I look up here, the domain of f was 0 to 2. That's got to be the range of f inverse. So up here, I'm going to say x equals 4 minus y squared for 0 is less than or equal to that y right there, because now I'm talking range, I'm talking y, and y is less than or equal to, and look at that upper bound, 2. And you guys see this right here. The y's in this inverse function are going from 0 to 2. Okay, awesome. So there we go. Y equals plus or minus root 4 minus x for 0 less than or equal to y, and y is less than or equal to 2. And because there are no negative values for this y right here, that means I can drop the minus. So it's just going to be y equals root 4 minus x. Okay, now inverse notation, and let's put everything in terms of x now. So y is actually the inverse of this function f up here. So I'm going to go f inverse of x equals root 4 minus x, okay? And now let's talk about this. The range of f becomes the domain of f inverse. So you see the range of f is this 0 to 4 right here. Well, that's the domain of the inverse function. This inverse function starts at x equals 0 and goes all the way to x equals 4. So I'm going to say, we're talking x's now, domain, and 0 is less than or equal to x, and x is less than or equal to 4. And there you have it. All right. So does f have an inverse? Yes, it does. And it's f inverse of x equals root 4 minus x. And the restricted domain would have to be 0 is less than or equal to x, and x is less than or equal to 4. Okay? Now, check that on a calculator. So here is my original function right here. And here's my line y equals x right here. Now, if I graph y sub 2 is root 4 minus x, and I do the interval from 0 to 4, look at what I get right there. The perfect reflection of my original function. Hey, that's almost as good as the one we drew by hand up above, too. Okay, so note, if the domain of f of x equals 4 minus x squared were the set of all real numbers, we could reflect that graph over the line y equals x, but that would not be a function, and I'm about to show you why. So, with that statement then, therefore, not all functions have inverse functions. You can reflect anything over a line y equals x, but that reflection may or may not be a function. Okay, so let's make the domain now all real numbers. So if I ask you right now, does that function have an inverse? You would tell me no, because it does not pass the horizontal line test. Okay, but we can still reflect it, and what do we reflect over? The line y equals x. So there's my line y equals x right there. And now let's pick some key points again. Interchange the coordinates, so I'd probably start with this vertex again right here. Oh, I did, and isn't that 0, 4 right there? Yes, it is. So that means on the reflection, I would have to have 4, 0, 1, 2, 3, 4. That point right there. Okay? And now, to reflect over that line y equals x, the other 2 points I would use are where my original parabola intersect with y equals x. So relations that are reflections in the line y equals x must intersect on y equals x. So I know I'm going to have another point right here and right there. Just like that. And with those 3 points, I can do a perfect parabola opening up to the left. Just like that right there. But unfortunately, that is a reflection, but that reflection is not the graph of a function because it does not pass the vertical line test. So the reflection of f in the line y equals x is not a function. It does not pass the vertical line test. Okay, so I just mentioned this on the previous slide. How do I check to see if a function has an inverse? I do this horizontal line test. If the graph of the function y equals f of x is such that no horizontal line intersects the graph in more than one point, then f is 1-to-1 and does have an inverse function. So let's draw a few graphs and see if we think we have an inverse. So this looks like it might be part of a cubic, I don't know, something like that. And does that look 1-to-1 to you guys? Or could you say, does that pass a horizontal line test? And do you agree, wherever I draw a horizontal line on this graph, it's only going to cross it at one point? Therefore, that y equals f of x does pass the horizontal line test. Therefore, that function has an inverse. F is 1-to-1 and has an inverse. Okay? Oh, now let's talk about the parabola that we just reflected. Does that pass the horizontal line test? No, it does not. So if I did f of x equals 4 minus x squared and I told you x was in the set of real numbers, you would tell me that that parabola does not have an inverse function, and you'd be correct. Unless, of course, we restricted its domain so it is 1-to-1. So it does not pass the horizontal line test. There is not an inverse to that function. But if I restrict the domain to 0 to 2, now we do pass the horizontal line test. And so that function does have an inverse. It's a parabola in a restricted domain, making it 1-to-1. Okay. Oh, now these are fun right here, okay? Analyzing function notation and inverse functions. So if I make the comment f of 2 equals 3, and then I ask you for f inverse of 3, well, what do you know? You know, inverse functions, what have we done? We have interchanged the variables, meaning on every point we have interchanged the coordinates. X becomes y and y becomes x. So if f of 2 equals 3, then f inverse of 3 would have to equal 2. And now I have f of f inverse of 3. Now, isn't that f of 2? And didn't you say above that f of 2 was 3? So this would have to be a 3. And now I have f inverse of f of 2. Well, one thing, inverses undo each other. So f inverse of f, those two functions are inverses. They undo each other, so I know this has to be 2. But you could do this like this too. F inverse of f of 2, well, what is f of 2? It's 3, so that becomes f inverse of 3. And we said right above here, f inverse of 3 equals 2. Okay, but we knew that just by looking. Inverse functions undo each other. So f inverse of f of 2 has to equal 2. Now, we're going to do this with functions. And I'm going to skip a few steps here. So if you need to write out a few extra steps, please do. And I'll do that in the classroom with you as well. Okay, so we're asked to find g inverse of x if, in case 1, g of x equals 4x. Okay, so what am I going to do? I'm going to interchange the variables. So the g of x becomes an x, and the x becomes a y. So x equals 4 times y. Now I just solve for y. But remember, y has to be written as inverse g of x. So this y right here becomes an inverse g of x. Solve for y and use inverse notation. So inverse g of x equals, and now just look at this and you can probably skip the steps just like I have. Well, what are we undoing here to solve for that y? Well, we're dividing by 4 or multiplying by 1/4. So that means this y, which is now inverse g of x, would have to equal 1/4 of x, or x over 4 if you prefer. Now let's do the same thing right here. So interchange the variables. The g of x is a y, that becomes an x, and x would have to equal 3y plus 2. All right? Now, solve for y, but what is y going to be? G inverse of x. And what would this y equal when I solve for it? Well, I'm going to say G inverse of x, this y right here, what would I do first? I would subtract the 2 and then divide by the 3. So that's going to be the quantity x minus 2 over 3. There you go. Now, let's do this again. Interchange the variables. G of x becomes x, and x becomes y. So x equals 2y minus 1. Now, if you solve this one for y, and how am I going to write the y? G inverse of x. Well, what would you do? You would add 1 and then divide by 2. So I see x plus 1 over 2. And then finally, g of x equals 4 minus 5x. All right, well, let's interchange the variables. So g of x becomes an x, and this x becomes a y. So I see x equals 4 minus 5y. Now, let's solve for this y, which we're going to write as g inverse of x. And if I solve for y, I would add the 4 and then divide by negative 5. So I could write x plus 4 over negative 5, but I don't like to divide by a negative like that. So x plus 4 over negative 5, could I write that as 4 minus x over 5? Just a little cleaner. There you have it. And if you need to see that step, write it out on your piece of paper. All right, kind of cool, huh? Okay, now, I want you to be able to visualize functions. So, and again, you could go to your calculator if you need to, but I'm hoping you're to the point where you don't. Like, I'm hoping everybody in this room can picture x to the third power. Okay, it's going to start in quadrant 3, work up to the origin, and then you'll see the shape of that triple root and finish in quadrant 1. Okay, so x to the third would again start down here in quadrant 3, go through the origin, triple root, and finish in quadrant 1. Now we're just going to slide that graph down 1 unit. There's y equals x to the third. There's y equals x to the third minus 1. And is that a one-to-one function? Well, look at just that red curve right there. Why, yes, it is. Okay, now let's do the same thing with g of x equals x to the third minus x. Now, let's get really good at visualizing this stuff. So I'm going to write that cubic binomial in factored form so I can see the roots. So I'm going to say 0 equals x to the third minus x. And in these two terms, I have a common factor of x. So I'm going to bring that out. X times what? X squared minus 1. And then I'm going to come over here and factor some more. So I have x times, and I hope you all see the difference of squares right there, x squared minus 1. And doesn't x squared minus 1 factor to x minus 1, x plus 1? Just like that. And now, look at these 3 factors and give me the 3 roots. The first root I see with this factor is a 0. The next root I see because of this factor would be a 1. And the final root that I see because of this factor would be a negative 1. Now, look at our original function right here, x to the third. That's 1x to the third. So that's a cubic that has to start down here in quadrant 3, go through the single root, take a turn, go through another single root, take a turn, and go through my final single root and finish up here in quadrant 1. There it is. Now, is that one-to-one? Obviously not. It does not pass the horizontal line test. Answer is no. Okay, so how can you obtain the Celsius function from the Fahrenheit function? Well, in a way, we've essentially already done it, all right? We put them into function notation and we interchange the variables. So if I have the Fahrenheit function and I want the Celsius function, what am I going to do? Well, write the function as y in terms of x. So can I write this as y equals 9/5 x plus 32? just like that. Then interchange the variables. So now this y becomes an x, and this x becomes a y. Solve for y. So if I'm going to solve for y, the first thing I'm going to do is subtract 32. Okay, oh, you know what I did? Okay, yeah, the 9/5 y is on the right. I'm writing that on the left, but then if I subtract the 32, aren't I now going to put x minus 32 over here on the right? And you could have written that x minus 32 equals 9/5 y, either way. All right, and now, again, solve for y. So we have to get rid of this multiplication by 9/5. Can I just multiply both sides by the reciprocal of 9/5? Which would be, what, 5/9? So 5/9 times 9/5 of y is y. And then I've got to take this side and multiply by 5/9. There it is right there. So y equals 5/9 times the quantity x minus 32. And what does y equal? F inverse of x. So F inverse of x, or our Celsius function, equals 5/9 times the quantity f minus 32. And there we go. Okay, let's visualize some more functions. So which of the following functions have inverses? Again, visualize the function and determine whether or not they are one-to-one. Okay? And when I talk so much about visualizing functions, that takes me back to a training I did in 1987 at Prairie High School. And the training was called Math in the Mind's Eye. Math in the Mind's Eye, okay? It's kind of deep stuff. But can you guys all visualize the absolute value of x? Close your eyes, take a deep breath, and think about it. Wouldn't that be the v function where this point right here is right at the origin? Why, yes, that's it. And would that pass a horizontal line test? No, it would not. No. Now, f of x equals x to the third. You don't have to go very deep into the mind's eye for this one, because we just graphed y equals x to the third. And that was the parabola beginning in quadrant 3, working to the origin with a triple root, and then finishing in quadrant 1. Something like that right there. And does that pass the horizontal line test? Why, yes, it does. And then f of x equals x to the fourth. Now, when I picture my parent of all quartic functions, y equals x to the fourth, I think of a broader y equals x squared. So this is going to look like a typical parabola, except it's going to be a lot broader. Something like that right there. And that's not drawn perfectly, but I can clearly see that that would not pass the horizontal line test. And what if I took that function and I restricted the domain? Like right now, x equals 0 is right here. So if I say x has to be less than or equal to 0, wouldn't that be just this part of this graph? Yeah, it would. And does this pass a horizontal line test? Why, yes, it does. Math in the Mind's Eye, Prairie High School, 1987. Thank you, Prairie. Okay. Well, my friends, I think that's got to be pretty close to it. Let's see. Oh, yeah. So I would like you guys today to do 4.5, and let's do these, 14 problems, 1 through 27 odd. And remember, your answers are in the back of your book. Thanks so much, and have a great day.